What if everything we know about the universe is just the tip of an unimaginable iceberg? The story of our cosmos begins with immense questions that even the brightest minds struggle to answer. From the moment the universe burst into existence to the formation of the first stars and galaxies, mysteries abound that defy our understanding. In this journey, we're diving deep into the enigmas of the early universe, exploring 50 of the most perplexing puzzles that challenge everything we think we know about reality. These aren't just scientific questions, they're profound mysteries that touch the very essence of existence itself. Why does the cosmos look the way it does? What secrets lie hidden in the void of space and time? And how did it all begin? Together, we'll unravel these cosmic riddles, shedding light on the darkest corners of the universe while embracing the wonder and curiosity that drive us to explore. Stay with me, because by the end of this video, you'll see the universe in a way you never have before. Let's go. Now, let's step into the very first mystery that sets the stage for everything we know or think we know about the universe. At the heart of the Big Bang Theory lies a mind-bending concept, the singularity. Imagine a single point, infinitely dense and unimaginably small, containing all the matter and energy that would one day become the cosmos. This is where our universe began, but here's the thing: our understanding of this moment is shrouded in mystery. What exactly does it mean for the universe to start as a singularity? How can something be infinitely dense? And perhaps the most baffling question of all, what existed before it? These are questions that even the most advanced physics can't yet answer. The laws of nature, as we know them, break down at this point. It's as if the universe itself is teasing us, hiding the truth of its origins behind an impenetrable veil. But here's what we do know: that singular moment set everything into motion, sparking the expansion of space, time, and matter. Yet the deeper we dig, the more questions we uncover. Was the Big Bang truly the beginning, or just one chapter in a much grander story? Stay with me as we unravel this cosmic enigma, because the journey is just getting started. Now let's turn our attention to the next cosmic puzzle, the theory of cosmic inflation. Picture this: less than a billionth of a trillionth of a second after the Big Bang, the universe didn't just expand, it exploded outward at an unimaginable speed. This rapid expansion, known as cosmic inflation, is thought to have stretched the fabric of space itself, smoothing out the universe and setting the stage for everything we see today. But how do we know this happened? One key piece of evidence lies in the cosmic microwave background, the faint glow left over from the Big Bang. This ancient light shows a remarkably uniform temperature across vast distances, something that can only be explained if the universe underwent a period of rapid inflation. Another clue comes from the large-scale structure of the cosmos. The way galaxies are distributed across the universe aligns with predictions made by inflation theory. Yet, despite the evidence, the cause of this dramatic expansion remains a mystery. What force could have driven the universe to inflate so quickly, and could inflation have happened more than once? These are questions that continue to challenge physicists, inviting us to rethink our understanding of the cosmos. As we piece together the story of cosmic inflation, we're reminded that the universe is full of surprises, each one bringing us closer to uncovering its deepest secrets. Now, let's explore another fascinating mystery of the early universe, the horizon problem. Imagine looking out at the night sky and noticing something strange. No matter which direction you gaze, the distant regions of the universe appear to have the same temperature. At first glance, this might not seem like a big deal, but when you consider the vast distances involved, it becomes a puzzle. These regions are so far apart that light, or any form of communication, wouldn't have had enough time to travel between them since the Big Bang. So how did they end up with the same temperature? This is the essence of the horizon problem. One of the most compelling explanations comes from the theory of cosmic inflation. According to this idea, the universe underwent a period of extremely rapid expansion in its earliest moments. This expansion would have stretched regions that were once close together, making them appear far apart today. Because they were originally in contact, they would have shared the same temperature. Inflation effectively smooths out the universe, explaining the uniformity we observe in the cosmic microwave background. However, while inflation provides a plausible solution, it also raises new questions. What triggered this rapid expansion, and could there be other explanations for the horizon problem? These mysteries keep scientists probing deeper into the fabric of the cosmos. As we uncover more about the horizon problem, we're reminded just how interconnected and intricate the universe truly is, inviting us to continue our quest for understanding. Moving forward, we arrive at one of the most perplexing enigmas of the cosmos, the nature of dark matter. Imagine a universe filled with something we can't see, yet it makes up most of the mass around us. Dark matter is this invisible substance, influencing everything from the rotation of galaxies to the large-scale structure of the universe itself. Unlike ordinary matter, it doesn't emit, absorb, or reflect light, making it nearly impossible to detect directly. But its presence is undeniable. When astronomers observed the way galaxies spin, they noticed something peculiar. The outer regions of galaxies were moving much faster than expected, suggesting the existence of a hidden mass holding them together. This invisible gravitational glue is dark matter. Without it, galaxies would simply fly apart. But what exactly is dark matter made of? Scientists have proposed several candidates, from weakly interacting massive particles, often called WIMP, to actions, ultra-light particles that could permeate the cosmos. Yet, despite decades of research, dark matter remains elusive. Experiments deep underground and in space are actively searching for it, hoping to catch a glimpse of this mysterious substance. Theories abound, but the true nature of dark matter continues to challenge our understanding of the universe. As we explore this invisible framework that shapes the cosmos, we're reminded of how much there is still to uncover. The quest to detect and understand dark matter is not just about solving a scientific puzzle, it's about unraveling the very fabric of reality itself, and with it, the story of our universe. Now, let's turn our attention to another cosmic puzzle that's just as baffling as dark matter: dark energy. Imagine the universe not just expanding, but doing so at an ever-increasing speed. This acceleration is driven by dark energy, a mysterious force that makes up about 68% of the universe's total energy. Unlike dark matter, which pulls things together through gravity, dark energy seems to push the universe apart. Its discovery in the late 1990s came as a shock to astronomers. By observing distant supernovae, scientists realized that the universe wasn't just expanding, it was doing so faster than expected. This observation turned our understanding of the cosmos on its head. So, what exactly is dark energy? One leading theory suggests it's a property of space itself, often referred to as the cosmological constant. This idea stems from Einstein's equations, though even he initially considered it a mistake. Another possibility is that dark energy is a dynamic field, changing over time and space, which would make it even more enigmatic. But here's the challenge: dark energy doesn't interact with light or matter in any way we can directly observe. It's inferred purely from its effects on the universe's expansion. This makes it incredibly difficult to study. Current missions like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to shed light on this elusive force by mapping the universe's large-scale structure and measuring the rate of expansion with unprecedented precision. Yet, despite these efforts, dark energy remains one of the greatest mysteries in modern cosmology. Its existence raises profound questions about the fate of the universe. Will dark energy continue to push galaxies apart indefinitely, leading to a cold, empty cosmos, or could it evolve in ways we can't yet predict? As we grapple with these questions, we're reminded once again of how little we truly understand about the forces shaping our universe. The mystery of dark energy isn't just about expansion, it's about the very fate of everything we know. Shifting our gaze to yet another cosmic enigma, we come face to face with a question that challenges the very fabric of our universe. Why is there so much more matter than antimatter? According to our current understanding of physics, every particle of matter should have an antimatter counterpart, identical in mass but opposite in charge. When matter and antimatter meet, they annihilate each other, releasing energy. So if the Big Bang created equal amounts of both, why does the universe we observe today consist almost entirely of matter? This is the mystery of the missing antimatter, and it's one of the most baffling puzzles in cosmology. Scientists call this imbalance baryogenesis, a process that must have occurred in the early universe to tip the scales in favor of matter. One leading theory suggests that certain conditions allowed matter particles to slightly outnumber antimatter particles, even if by just 1 part in a billion. But what could have caused this? Physicists have proposed several possibilities, including phenomena like CP violation, where particles and their antimatter counterparts behave differently under certain conditions. Experiments like those conducted at the Large Hadron Collider are tirelessly searching for clues, probing the behavior of particles to understand why matter won the cosmic lottery. Another theory points to the role of neutrinos, those elusive ghost particles, which might have played a part in this imbalance. Yet, despite decades of research, the answer remains elusive. This mystery isn't just about answering a scientific question, it's about understanding why the universe exists as we know it. Without this imbalance, matter and antimatter would have annihilated each other entirely, leaving behind a barren, lifeless void. As we continue to explore this cosmic riddle, we're reminded once again of how delicate and finely tuned the universe truly is. The search for the missing antimatter isn't just about solving a puzzle, it's about uncovering the very origins of everything we see around us. Now let's journey even further back in time to a moment when the universe was completely dark, a time before stars or galaxies illuminated the cosmos. This brings us to the mystery of the first stars and galaxies, often referred to as population 3 stars. These ancient celestial objects were the universe's first light, born from the primordial gas left over after the Big Bang. Unlike the stars we see today, which are rich in heavy elements like carbon and oxygen, population 3 stars were composed almost entirely of hydrogen and helium, the simplest and lightest elements in existence. Their formation marked a turning point in cosmic history, ending the era known as the Cosmic Dark Ages. As these first stars ignited, they began to reshape the universe around them. Their intense ultraviolet radiation ionized the surrounding hydrogen gas, a process known as reionization, which gradually transformed the universe from opaque to transparent. The light from these stars traveled across vast distances, illuminating the early cosmos and setting the stage for the formation of the first galaxies. But why are these population 3 stars so elusive to modern astronomers? The answer lies in their age and distance. These stars existed billions of years ago, and their light has been stretched by the expansion of the universe, shifting it into the infrared spectrum, which is harder to detect. Additionally, many of these stars likely exploded as supernova in their early lifetimes, scattering heavy elements into space and seeding the universe for future generations of stars. Yet their legacy lives on. The elements forged in their cores became the building blocks for everything that followed, from planets to life itself. Studying population 3 stars isn't just about exploring the origins of light in the universe. It's about understanding how the cosmos evolved from simplicity to complexity, 1 star at a time. As we peer deeper into the early universe, we're reminded that these ancient stars were the pioneers, lighting the way for everything that came after. Building on the story of those first stars, let's explore the profound changes they brought to the early universe. This leads us to the epoch of reionization, a pivotal era when the cosmos underwent a dramatic transformation. After the Big Bang, the universe was filled with neutral hydrogen gas, making it opaque to light. But as those first population 3 stars ignited, their intense ultraviolet radiation began to ionize the surrounding hydrogen, stripping electrons from atoms and turning the gas into a sea of charged particles. This process, known as reionization, gradually made the universe transparent, allowing light to travel freely across vast distances. It's a defining chapter in cosmic history, shaping the universe into the one we observe today. Yet, studying this epoch presents significant challenges. The light from this era is incredibly faint and has been stretched into the infrared by the expansion of the universe, making it difficult to detect. Additionally, the sources of this ionization, the first stars and galaxies, are themselves elusive, often hidden behind layers of cosmic dust and gas. Astronomers rely on indirect methods, such as observing the absorption of light by distant quasars or studying the cosmic microwave background, to piece together the story of reionization. Despite these obstacles, understanding this period is crucial, as it bridges the gap between the universe's dark beginnings and its current luminous state. The epoch of reionization reminds us that even the faintest light can illuminate the darkest corners of the cosmos, revealing the intricate processes that shape the universe we call home. Now let's turn our attention to a relic of the early universe, one that serves as a cosmic fingerprint of its origins, the cosmic microwave background. This faint glow, often called the afterglow of the Big Bang, is the oldest light we can observe, dating back to when the universe was just 380,000 years old. At that time, the universe had cooled enough for protons and electrons to combine into neutral hydrogen, allowing light to travel freely for the first time. This light, initially blazing hot, has been stretched by the expansion of the universe over billions of years, now appearing as a faint microwave radiation that permeates the cosmos. The CMB is like a time capsule, preserving a snapshot of the universe in its infancy, and it has become one of the most powerful tools for understanding the Big Bang and the conditions that followed. What makes the CMB particularly fascinating is its near-perfect uniformity. Across the sky, the temperature of this background radiation is remarkably consistent, varying by only tiny fractions of a degree. This uniformity supports the Big Bang theory and provides evidence for cosmic inflation, the rapid expansion of the universe in its earliest moments. However, the CMB also holds mysteries that challenge our understanding. Subtle anomalies, such as unexpected temperature fluctuations and alignments in the radiation, have been detected, defying current cosmological models. For instance, a strange cold spot in the CMB has puzzled scientists, with some suggesting it could be evidence of a collision with another universe, though this remains speculative. These anomalies remind us that, while the CMB has illuminated much about the universe's beginnings, it also raises questions that push the boundaries of our knowledge. By studying the CMB, astronomers can map the early distribution of matter and energy, tracing the seeds of galaxies and cosmic structures we see today. Yet, the anomalies within it hint at deeper layers of the universe's story, waiting to be uncovered. The cosmic microwave background is not just a window into the past, it's a puzzle, inviting us to explore the mysteries that still linger in the echoes of the Big Bang. As we continue to probe its secrets, we inch closer to understanding the universe's true nature, one photon at a time. Now, let's journey into the vast architecture of the cosmos with a look at the Great Cosmic Web. This immense structure, often described as the universe's skeleton, is a sprawling network of filaments and voids that connects galaxies and galaxy clusters across billions of light years. Picture it as a spider's web on a cosmic scale, where threads of matter stretch across the emptiness of space, weaving together the fabric of the universe. The cosmic web didn't form overnight. Its intricate patterns are the result of gravity's relentless pull acting on the seeds of matter and energy planted during the Big Bang. These seeds, tiny fluctuations in density, grew over billions of years as gravity drew matter together into dense regions while leaving others nearly empty. Dark matter, the mysterious substance that makes up most of the universe's mass, played a crucial role in this process. Although invisible, its gravitational influence guided the formation of these cosmic threads, while ordinary matter, the stuff we can see, followed suit, clumping together to form stars, galaxies, and eventually the web we observe today. What makes the cosmic web so fascinating is its ability to reveal the universe's hidden structure. Galaxies aren't scattered randomly. They gather along these filaments like pearls on a string with vast voids in between. These voids, regions of near emptiness, make up most of the universe's volume, creating a stark contrast to the dense filaments. Together, they form a delicate balance, a testament to the interplay of gravity and dark matter over cosmic time. Yet the cosmic web also raises questions. How did it evolve into its current form? What role did dark energy play in shaping its expansion? And what lies within the voids? Are they truly empty, or do they hide undiscovered phenomena? By mapping this web, astronomers can trace the universe's growth and better understand the forces that shaped it. It's a reminder that the cosmos is more than a collection of isolated objects. It's a connected, dynamic system, woven together by the threads of gravity and the unseen hand of dark matter. As we explore the great cosmic web, we're not just charting the universe's structure, we're uncovering the story of how it came to be, one filament and void at a time. Turning our gaze toward the future, we now explore one of the most profound mysteries of all, the fate of the universe. What awaits the cosmos as it continues to expand and evolve? Scientists have proposed several compelling theories, each painting a different picture of how the universe might meet its end. One possibility is the Big Crunch, a dramatic reversal of the Big Bang. In this scenario, the universe's expansion slows down, stops, and eventually collapses back in on itself. Imagine the cosmos contracting into a single, dense point, much like it began. This theory hinges on the balance between gravity and dark energy, the mysterious force driving the universe's accelerated expansion. If gravity were to overcome dark energy, pulling everything back together, the Big Crunch could become reality. On the other hand, there's the theory of heat death, also known as the Big Freeze. Here, the universe continues to expand indefinitely, with galaxies drifting farther and farther apart until they are isolated islands in an ever-growing void. Stars burn out, black holes evaporate, and the universe becomes a cold, dark, and lifeless place. This scenario suggests that dark energy will dominate, driving the cosmos toward a state of maximum entropy where no usable energy remains. Then there's the Big Rip, a more dramatic version of the heat death. In this theory, dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms themselves. It's a cataclysmic end where the fabric of space-time itself is shredded. These theories hinge on our understanding of dark energy, a force that remains one of the greatest enigmas in cosmology. What is it exactly, how does it work, and how will it shape the universe's destiny? While we don't yet have all the answers, studying dark energy and its effects on cosmic expansion could hold the key to predicting the universe's ultimate fate. As we ponder these possibilities, we're reminded that the universe's story is far from over. Its fate is still being written, shaped by forces we are only beginning to understand. The journey to uncover these answers continues, offering us a glimpse into the grand narrative of existence itself. Now, shifting our perspective to an even grander scale, let's venture into the intriguing concept of the multiverse hypothesis. Imagine not just one universe but countless others, each with its own unique set of physical laws, constants, and even realities. This idea challenges our understanding of existence itself. suggesting that our universe might be just one thread in a vast cosmic tapestry. The multiverse hypothesis arises from several areas of theoretical physics, including quantum mechanics, string theory, and cosmic inflation. For instance, in the context of cosmic inflation, it's possible that the rapid expansion of the early universe created bubbles, each giving rise to its own distinct universe. These universes could exist parallel to ours, completely disconnected yet part of the same cosmic framework. Another line of evidence comes from quantum mechanics, where the many worlds interpretation proposes that every possible outcome of a quantum event spawns a new universe. This means that every decision, every random event could create a branching path of realities, each playing out slightly differently. But what does this mean for us? Philosophically, the multiverse hypothesis challenges the notion of uniqueness. If there are infinite universes, does that mean every possible version of reality exists somewhere? It's a mind-bending idea that not only reshapes our understanding of the cosmos, but also raises profound questions about our place within it. While the multiverse remains a theoretical concept, it's a compelling area of study that pushes the boundaries of science and imagination. As we continue to explore the mysteries of the universe, the possibility of a multiverse reminds us just how vast and complex reality might truly be. Turning our attention to the tiniest scales of existence, let's explore the quantum origins of the universe. At the heart of this mystery lies the idea that the birth of the cosmos might be rooted in the strange and unpredictable world of quantum mechanics. This theory suggests that the universe began not as a smooth, singular event, but as a product of quantum fluctuations, tiny, random changes in energy that occur on the smallest scales imaginable. At the moment of the Big Bang, these fluctuations could have played a crucial role in shaping the early universe. Imagine a sea of energy, constantly shifting and bubbling, and from this chaos, the seeds of galaxies, stars, and planets emerged. These quantum fluctuations, though incredibly small, set the stage for the vast structures we see in the cosmos today. One of the key pieces of evidence supporting this idea comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny variations in this ancient light reflect the early quantum fluctuations, which later grew into the large-scale structures of the universe. It's a remarkable connection between the microscopic and the cosmic, showing how the universe's origins might be deeply tied to the rules of quantum physics. But how did these fluctuations lead to the universe we know? As the universe expanded, these tiny irregularities were stretched out, creating regions of slightly higher and lower density. Over billions of years, gravity amplified these differences, pulling matter together to form galaxies and clusters. In this way, the smallest quantum events became the blueprint for the entire cosmos. The concept of quantum origins also raises fascinating questions about the nature of reality itself. If the universe began with random fluctuations, does that mean our existence is a product of chance? Or is there a deeper order underlying these seemingly chaotic processes? While the quantum origins of the universe remain a subject of intense study, they offer a compelling glimpse into the forces that shaped existence. As we continue to unravel these mysteries, we're reminded that even the smallest phenomena can have the most profound consequences. Now, let's move forward to another intriguing puzzle, the possibility of primordial black holes and their mysterious role in the early universe. Shifting our focus to another cosmic enigma, let's delve into the possibility of primordial black holes. These hypothetical objects are thought to have formed in the earliest moments of the universe, long before the first stars and galaxies came into existence. Unlike the black holes we're familiar with, which are born from the collapse of massive stars, primordial black holes could have emerged directly from the extreme density and energy of the early cosmos. One fascinating idea is that these black holes might be linked to the mysterious substance known as dark matter. While dark matter makes up a significant portion of the universe's mass, its exact nature remains unknown. Primordial black holes, if they exist, could provide a compelling explanation. These ancient black holes scattered throughout the cosmos might account for some or even all of dark matter's invisible presence. However, detecting primordial black holes is no easy task because they are incredibly dense and compact. They don't emit light or radiation, making them nearly impossible to observe directly. Instead, scientists rely on indirect methods, such as searching for their gravitational effects on surrounding matter or looking for brief flashes of light caused by their interactions with stars. Another challenge lies in their potential size range. Primordial black holes could vary dramatically in mass, from as small as a speck of dust to as massive as a planet. This wide range complicates efforts to identify them, as different detection techniques are needed for different sizes. Despite these challenges, the hunt for primordial black holes continues, driven by the tantalizing possibility that they could unlock secrets about the universe's beginnings and the nature of dark matter. If discovered, they would not only reshape our understanding of the cosmos, but also provide a window into the extreme conditions that existed just moments after the Big Bang. As we explore this mystery, we're reminded of how much remains hidden in the vastness of space, waiting to be uncovered. Next, we'll turn our attention to another perplexing question: why matter dominates over antimatter in the universe. Turning our gaze to another profound mystery, we now explore the baryon asymmetry problem. This is the puzzling question of why there is so much more matter than antimatter in the universe. According to our understanding of physics, the Big Bang should have created equal amounts of matter and antimatter. Yet, when we look around, we see a cosmos filled almost entirely with matter, with antimatter being incredibly rare. So, what happened to all the antimatter? Scientists believe that some process in the early universe tipped the scale in favor of matter, but the exact mechanism remains elusive. This imbalance is known as baryon asymmetry, and solving it could reveal fundamental truths about the universe's origins. One leading theory involves a phenomenon called CP violation, which describes how particles and their antimatter counterparts behave differently under certain conditions. If CP violation occurred in the early universe, it might have allowed matter to dominate over antimatter. To test this idea, researchers are conducting experiments at places like CERN, the European Organization for Nuclear Research. At CERN, scientists use the Large Hadron Collider to recreate conditions similar to those just after the Big Bang. By smashing particles together at incredibly high speeds, they can study how matter and antimatter interact. These experiments have already revealed hints of CP violation in some particles, but the findings are not yet enough to fully explain the cosmic imbalance. Another approach involves studying neutrinos, particles that are nearly massless and rarely interact with matter. Some theories suggest that neutrinos could be their own antiparticles, a property that might have played a role in the matter-antimatter asymmetry. Experiments like those at CERN Neutrino Observatory aim to uncover more about these mysterious particles and their potential role in the early universe. The search for answers continues, driven by the hope that understanding baryon asymmetry could unlock secrets about the universe's first moments. As we ponder this mystery, we're reminded of how the cosmos defies our expectations, challenging us to think deeper and explore further. Next, we'll examine another cosmic puzzle, the Hubble tension, which reveals a surprising discrepancy in our measurements of the universe's expansion. Shifting our focus to another cosmic puzzle, we now turn our attention to the Hubble tension. This is a fascinating discrepancy in our measurements of the universe's expansion rate, which has left scientists scratching their heads. When we measure how quickly the universe is expanding, a value known as the Hubble constant, we get different results depending on the method we use. One approach involves observing nearby objects like Cepheid variable stars and Type 1, a supernova, to calculate the expansion rate. Another method looks at the cosmic microwave background, the afterglow of the Big Bang, to infer how fast the universe is stretching. Both techniques are precise and well established, yet they give different answers. This inconsistency is what we call the Hubble tension, and it's become a major challenge in modern cosmology. What makes this tension so intriguing is its potential to reshape our understanding of the universe. If the discrepancy is real and not due to measurement errors, it could mean there's something fundamental we're missing. Perhaps there's an unknown ingredient in the cosmos, like a new form of dark energy that's influencing the expansion rate. Or maybe our current understanding of gravity, as described by Einstein's theory of relativity, needs to be revised. Efforts to solve this mystery are ongoing. Researchers are developing new observational techniques and refining existing ones to reduce uncertainties. For example, gravitational waves from merging neutron stars could provide an independent way to measure the Hubble constant. Additionally, scientists are exploring the possibility that early universe physics might have left subtle imprints that we've yet to detect. The Hubble tension isn't just a technical disagreement, it's a window into the deeper mysteries of the cosmos. By tackling this challenge, we could uncover new physics that transforms our understanding of space, time, and the universe's evolution. As we continue to investigate, we're reminded that even our most trusted models can be appended, driving us to explore further and think bigger. Next, we'll explore the era of the first light and how it marked the universe's transition from darkness to illumination. Now, let's journey back to a pivotal moment in cosmic history, the era of the first light. This was the time when the universe emerged from its dark ages, a period shrouded in hydrogen gas, and began to glow with the birth of its earliest stars and galaxies. Picture a cosmos that had been pitch black for hundreds of millions of years, suddenly coming alive with the first flickers of light. The first light marked the end of the cosmic dark ages, a phase that followed the Big Bang and the release of the cosmic microwave background. During this time, the universe was filled with neutral hydrogen, a gas so dense it absorbed all light, leaving the cosmos in utter darkness. But as the first stars ignited, their intense ultraviolet radiation ionized this hydrogen, gradually transforming the universe into the transparent, glowing expanse we know today. This transformative process is known as reionization. Studying the era of the first light is no easy feat. Astronomers rely on some of the most advanced tools and techniques to peer back in time. One key method involves observing the most distant galaxies, whose light has traveled billions of years to reach us. By analyzing this ancient light, scientists can piece together how and when these early stars and galaxies formed. Another approach uses quasars, incredibly bright objects powered by supermassive black holes. Their light acts like a cosmic flashlight, illuminating the hydrogen gas that once filled the universe. However, there are still many unanswered questions. For instance, how exactly did the first stars form, and what were they like? Were they vastly different from the stars we see today? And what role did the first galaxies play in shaping the universe's structure? These mysteries drive ongoing research, with next-generation telescopes like the James Webb Space Telescope poised to provide unprecedented insights into this crucial epoch. The era of the first light was a turning point for the cosmos, setting the stage for the universe we inhabit today. By unraveling its secrets, we not only learn about the origins of stars and galaxies, but also gain a deeper understanding of how the universe evolved from its dark, formative years into the vibrant, illuminated cosmos we now observe. Next, we'll turn our attention to quasars, the brightest objects in the universe, and their role in the early universe's story. Now, shifting our focus to one of the most dazzling phenomena in the cosmos, let's dive into the mystery of quasars. These incredibly bright objects are like cosmic lighthouses, shining across the vastness of space and time. Quasars, short for quasi-stellar radio sources, are among the most luminous objects in the universe, outshining entire galaxies despite their relatively small size. But what exactly are they, and how did they come to be? Quasars are powered by supermassive black holes which lie at the centers of distant galaxies. As these black holes devour surrounding gas and dust, they release an immense amount of energy in the form of light and radiation. This process creates a brilliant glow that can be seen from billions of light years away. The sheer power and brightness of quasars make them invaluable tools for studying the early universe, as their light provides a glimpse into conditions that existed billions of years ago. But how did these supermassive black holes form so early in the universe's history? One theory suggests that they grew from smaller black holes that merged and accumulated mass over time. Another idea is that they formed through the direct collapse of massive clouds of gas, bypassing the star formation process entirely. Regardless of their origins, quasars played a crucial role in shaping the cosmos. Their intense radiation helped ionize the hydrogen gas that filled the early universe, contributing to the epoch of reionization. This process cleared the cosmic fog, allowing light to travel freely and setting the stage for the universe we see today. Quasars also influenced the formation of galaxies, as their energy regulated star formation and drove the evolution of cosmic structures. Despite their brilliance, quasars remain shrouded in mystery. How exactly did they form so quickly after the Big Bang? What mechanisms sustain their incredible energy output, and what can they tell us about the nature of supermassive black holes? These questions continue to drive astronomical research, with advanced telescopes and simulations offering new insights into these enigmatic objects. Quasars are not just fascinating in their own right, they also serve as cosmic beacons, illuminating the distant past and helping us piece together the story of the universe's evolution. Next, we'll explore the enigmatic formation of supermassive black holes and their role in the early cosmos. Turning our attention to another cosmic enigma, let's delve into the mystery of how supermassive black holes formed so quickly after the Big Bang. These colossal objects, often weighing billions of times the mass of our Sun, appeared in the early universe at a speed that challenges our understanding of cosmic evolution. How could such massive structures emerge in what seems like the blink of an eye on the universe's timescale? One leading theory suggests that supermassive black holes formed through a process known as direct collapse. In this scenario, massive clouds of gas, rather than collapsing into stars, instead collapsed directly into a black hole. This would bypass the typical star formation process, allowing for the rapid accumulation of mass. These primordial black holes could then grow further by merging with others or by drawing in vast amounts of surrounding gas and dust. Another possibility is that smaller black holes formed first, perhaps from the remnants of the universe's earliest stars. Over time, these black holes merged and accumulated mass, eventually becoming the supermassive giants we observe today. However, this process would require an extraordinary rate of growth to reach such colossal sizes so quickly, leaving astronomers puzzled about the exact mechanisms involved. Observing these early supermassive black holes is no easy task. Their light has traveled billions of years to reach us, and much of it is obscured by the dust and gas that surrounds them. Yet, advanced telescopes and simulations continue to provide clues. For example, the detection of distant quasars powered by supermassive black holes offers a glimpse into their early formation and growth. Understanding the origins of supermassive black holes is crucial because they played a pivotal role in shaping the universe. Their immense gravity influenced the formation of galaxies, and their energy output helped ionize the surrounding gas, paving the way for the cosmos we see today. As we explore this mystery further, we're reminded of how much there is still to learn about the early universe. Next, we'll uncover the role of neutrinos, the elusive ghost particles, in the unfolding story of cosmic evolution. Now, let's shift our focus to one of the most elusive players in the cosmic drama, neutrinos, often called the ghost particles of the universe. These tiny, nearly massless particles are incredibly difficult to detect, yet they played a crucial role in shaping the early universe. Born in the fiery aftermath of the Big Bang, neutrinos were among the first particles to fill the cosmos, and their influence can still be felt today. Neutrinos are unique because they interact extremely weakly with matter. Billions of them pass through your body every second without you ever noticing. This ghostly nature makes them challenging to study, but it also means they carry pristine information about the universe's earliest moments. In the dense, hot environment of the early universe, neutrinos moved freely, helping to distribute energy and influence the growth of cosmic structures. One of their most significant roles was in the era of nucleosynthesis, when the first atomic nuclei formed. Neutrinos affected the delicate balance of protons and neutrons, shaping the abundance of light elements like hydrogen and helium. Without their subtle influence, the chemical makeup of the universe might look very different today. Neutrinos also played a part in the cosmic microwave background, the afterglow of the Big Bang. As the universe expanded and cooled, these particles left faint imprints on this primordial radiation, providing scientists with clues about their properties and behavior. Modern experiments like neutrino observatories buried deep underground aim to detect these ancient particles and unlock their secrets. Understanding neutrinos is not just about studying the past, it's also about unraveling the present. For example, neutrinos produced in the cores of stars and during supernova explosions can tell us about the inner workings of these cosmic powerhouses. By studying their properties, scientists hope to solve some of the biggest questions in physics, from the nature of dark matter to the asymmetry between matter and antimatter. The story of neutrinos reminds us that even the smallest particles can have a monumental impact on the universe. As we continue to explore their mysteries, we gain deeper insights into the forces that shaped everything around us. Next, we'll turn our attention to another cosmic phenomenon, cosmic strings, mysterious one-dimensional defects that may hold the key to understanding the universe's grand structure. Now, let's explore a mind-bending concept that stretches our understanding of the cosmos, cosmic strings. These are hypothetical one-dimensional defects in the fabric of space-time, thought to have formed during the early universe's rapid cooling after the Big Bang. Imagine the universe as a vast, intricate tapestry and cosmic strings as tiny, thread-like irregularities woven into its fabric. These cosmic threads, though incredibly thin, could stretch across unimaginable distances, potentially reaching from one end of the universe to the other. Cosmic strings are theorized to be remnants of symmetry breaking, a process that occurred as the universe transitioned from a hot, dense state to the cooler, more structured one we see today. During this phase, the fundamental forces of nature separated, and cosmic strings may have formed as a byproduct. If they exist, these strings would be unimaginably dense, carrying immense amounts of energy within their slender forms. One of the most intriguing aspects of cosmic strings is their potential role in shaping the universe's large-scale structure. They could have acted as cosmic seeds, influencing the formation of galaxies and galaxy clusters by creating gravitational ripples that pulled matter together. Some theories even suggest that cosmic strings might be responsible for anomalies in the cosmic microwave background, the afterglow of the Big Bang, providing indirect evidence of their existence. Detecting cosmic strings is no easy task given their elusive nature. However, scientists have proposed several methods to spot them. One approach involves looking for gravitational lensing effects, where the immense gravity of a cosmic string bends light from distant objects, creating double images or distortions in the sky. Another method relies on searching for gravitational waves, ripples in space-time, which cosmic strings might produce as they oscillate or collide. While cosmic strings remain hypothetical, their discovery would revolutionize our understanding of the universe's origins and evolution. They could shed light on the fundamental forces of nature and provide clues about the conditions that existed in the universe's earliest moments. As we continue to probe the cosmos for these elusive threads, we inch closer to unraveling one of the most profound mysteries of the early universe. Next, we'll delve into another pivotal moment in cosmic history, the end of the Dark Ages, when the first stars and galaxies began to illuminate the cosmos. Shifting our focus to a transformative era in cosmic history, we arrive at the end of the Dark Ages, a period when the universe emerged from its shadowy beginnings into a luminous dawn. For hundreds of millions of years after the Big Bang, the universe was a cold, dark void filled with hydrogen gas but devoid of light. This epoch, known as the Cosmic Dark Ages, was a time of stillness with no stars, galaxies, or sources of illumination to pierce the darkness. Then something extraordinary happened. The first stars ignited, their light cutting through the cosmic gloom and heralding a new chapter in the universe's story. These early stars, often referred to as population 3 stars, were unlike any we see today. They were massive, hot, and short-lived, composed almost entirely of hydrogen and helium, the only elements present in the early universe. Their intense radiation began to ionize the surrounding hydrogen gas, gradually transforming the universe from a neutral state to one filled with charged particles. This process, known as the epoch of reionization, marked the end of the Dark Ages and the beginning of the universe as we know it. Over time, these first stars grouped together to form the earliest galaxies, setting the stage for the rich tapestry of cosmic structures we observe today. However, studying this pivotal era is no simple task. The light from these first stars and galaxies is incredibly faint and has traveled for billions of years to reach us. To detect it, astronomers rely on powerful telescopes capable of observing in infrared wavelengths, which can penetrate the cosmic dust and reveal the distant past. Challenges also arise from the interference of closer, brighter objects, which can obscure the already dim signals from the early universe. Despite these obstacles, scientists are making remarkable progress. Observations from space telescopes and ground-based observatories are beginning to piece together this critical period, offering glimpses into how the universe transitioned from darkness to light. Every discovery brings us closer to understanding how the first stars and galaxies shaped the cosmos and set the stage for the universe we inhabit today. Next, we'll explore another fascinating aspect of the early universe, the nature of time and how it might have behaved differently in those primordial moments. Now, let's turn our attention to one of the most enigmatic aspects of the early universe, the very nature of time itself. In the moments following the Big Bang, the universe was a place of extreme density and energy, a realm where the rules of physics as we know them may not have applied. Under such conditions, time itself might have behaved in ways that defy our everyday understanding. One of the most intriguing theories suggesting this possibility is quantum gravity. In the early universe, the intense gravitational forces and the quantum nature of particles could have created a scenario where time was not a smooth, continuous flow, but rather something more fluid and unpredictable. Quantum gravity attempts to bridge the gap between Einstein's theory of general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles at the smallest scales. In this framework, time might have been quantized, meaning it could have existed in discrete chunks rather than an unbroken continuum. Imagine time as a series of individual frames in a movie, each representing a tiny, fundamental unit of time. These frames, known as Planck time, are so brief, lasting about 10 to the power of -43 seconds, that they are impossible to observe directly. Yet, if this theory holds, it suggests that time in the early universe was not the steady, unyielding force we experience today, but instead a flickering, fragmented phenomenon. Another fascinating idea is that time itself could have evolved as the universe expanded. In the earliest moments, time might have been entangled with space in a way that blurred the distinction between the two. As the universe cooled and expanded, time could have gradually separated and taken on the linear, forward-moving nature we associate with it today. This evolution of time could explain why the early universe appears so different from the one we inhabit now. These theories are not just abstract speculations, they have profound implications for our understanding of the cosmos. If time behaved differently in the early universe, it could help explain some of the mysteries we've already explored, such as the horizon problem or the rapid expansion of cosmic inflation. It also challenges us to rethink our most fundamental assumptions about the nature of reality. As we continue to investigate the early universe, the question of how time operated in those primordial moments remains a tantalizing puzzle. It reminds us that even the most basic aspects of our existence, like the passage of time, might have origins far stranger and more complex than we ever imagined. Up next, we'll delve into the formation of the first molecules, exploring how the building blocks of chemistry emerged in the infant universe. As we shift our gaze from the peculiar nature of time in the early universe, let's turn to the very first molecules that began to shape the cosmos. In the aftermath of the Big Bang, the universe was a seething cauldron of energy and particles, but as it cooled, the stage was set for the formation of the simplest molecules, hydrogen and helium. These two elements were the first to emerge, born from the fusion of protons and neutrons in the early moments of the universe. Hydrogen, the lightest and most abundant element, made up about 75% of the matter in the early cosmos, while helium accounted for nearly 25%. Together, they laid the foundation for all the chemistry that would follow. The formation of these first molecules was no simple process. In the intense heat of the early universe, atoms were too energetic to bond together. It wasn't until the universe cooled enough around 300,000 years after the Big Bang that electrons could latch onto nuclei, forming stable hydrogen and helium atoms. This period, known as recombination, marked the first time the universe became transparent to light, allowing photons to travel freely and giving rise to the cosmic microwave background we observe today. But even after recombination, the journey of these molecules wasn't over. Cold, dense regions of gas began to clump together under the force of gravity, creating the first stars and galaxies. Within these stellar nurseries, hydrogen and helium atoms collided and bonded, forming the first diatomic molecules, molecular hydrogen or H2. Molecular hydrogen played a crucial role in the evolution of the cosmos. It acted as a coolant, allowing gas clouds to collapse further and ignite the first stars. These stars, in turn, fused hydrogen and helium into heavier elements, seeding the universe with the building blocks of life. Without these first molecules, the universe would have remained a barren expanse of atomic gas, unable to form the intricate structures we see today. The story of the first molecules is more than just a tale of cosmic chemistry. It's a reminder of how even the simplest ingredients can give rise to complexity and beauty. As we continue our journey through the mysteries of the early universe, we'll explore how these molecules paved the way for the first stars and galaxies, setting the stage for the universe as we know it. Now, as we venture further into the cosmic story, let's unravel the mystery of the first heavy elements. While hydrogen and helium laid the groundwork for the universe's chemistry, it was the birth of heavier elements like carbon and oxygen that truly set the stage for complexity. But where did these elements come from? The answer lies in the fiery hearts of the first stars and the cataclysmic explosions that ended their lives. When the first stars ignited, they fused hydrogen and helium into heavier elements through a process called stellar nucleosynthesis. Deep within their cores, extreme temperatures and pressures forced atomic nuclei to collide and merge, creating elements like carbon, oxygen, and even iron. These elements were forged in the crucible of stellar furnaces, marking the first time the universe produced anything beyond the simplicity of hydrogen and helium. However, these heavy elements remained trapped inside the stars until their dramatic deaths. When massive stars exhaust their nuclear fuel, they explode in spectacular supernova, scattering their enriched contents across the cosmos. These explosions not only released carbon, oxygen, and other heavy elements, but also created even heavier elements like gold and uranium through the intense heat and pressure of the blast. Supernovae were the universe's recycling centers, dispersing the building blocks of planets, life, and even future stars into the void. Without them, the universe would have remained a sea of hydrogen and helium, incapable of forming the complex structures and chemistry we see today. The formation of heavy elements also had a profound impact on the evolution of galaxies. As these elements mixed with interstellar gas, they provided the materials for new generations of stars and planets. Carbon and oxygen, in particular, became essential for the chemistry of life, setting the stage for the emergence of planets like Earth billions of years later. This puzzle of the first heavy elements is a testament to the interconnectedness of the cosmos. From the first stars to the explosions that scattered their remains, every step in this process was crucial in shaping the universe into the rich, diverse tapestry we observe today. As we continue our journey through the mysteries of the early universe, we'll explore how these heavy elements paved the way for the cosmos' ongoing evolution. Now, shifting our focus from the stars and their explosive legacies, let's turn our attention to the mystery of the first planets. Could planets have formed in the early universe, and if so, how would they have differed from the worlds we know today? This question takes us into uncharted territory, challenging our understanding of planetary formation and the timeline of cosmic evolution. In the modern universe, planets form within debris disks surrounding young stars, where dust and gas gradually clump together to create rocky or gaseous bodies. But in the early universe, the conditions were vastly different. The first stars, known as population 3 stars, were massive and short-lived, often ending their lives in spectacular supernovae. These early stars lacked the heavy elements necessary to form planets as we know them, since the universe was still mostly composed of hydrogen and helium. However, as the first stars exploded, they seeded the cosmos with the heavy elements forged in their cores. This enrichment process allowed for the possibility of planet formation in subsequent generations of stars. The first planets, if they existed, would have been incredibly primitive compared to modern worlds. They likely formed in systems with fewer heavy elements, meaning their compositions could have been dominated by hydrogen, helium, and simple compounds like water and methane. These ancient planets might have lacked the complexity and diversity of minerals and metals found on Earth and other modern planets. Another key difference lies in their environments. The early universe was far more chaotic, with frequent supernovae, intense radiation, and violent interactions between young stars and their surroundings. Planets forming in such a turbulent era would have faced extreme conditions, possibly influencing their atmospheres, geology, and even their potential to support life. While direct evidence of the first planets remains elusive, astronomers are actively searching for clues. By studying ancient star systems and analyzing the chemical compositions of the oldest stars, scientists hope to piece together the story of how and when planets first emerged in the cosmos. The mystery of the first planets not only challenges our understanding of planetary formation, but also raises profound questions about the timeline of cosmic evolution. As we continue to explore the early universe, we'll uncover more about how these ancient worlds shaped the path toward the diverse and complex cosmos we inhabit today. Stay tuned as we delve further into the mysteries that define the dawn of existence. Moving from the mystery of the first planets, let's now explore the enigmatic role of magnetic fields in the early universe. These invisible forces may seem subtle, but they played a crucial part in shaping the cosmos as we know it. Magnetic fields are everywhere in the universe today, from the expanse of galaxies to the confines of our own solar system. But how did they first arise in the early universe? Scientists believe that magnetic fields emerged during the chaotic conditions of the Big Bang or shortly after, possibly generated by the intense heat and density of the primordial plasma. Another theory suggests that they were seeded by the turbulent motions of gas and the powerful jets emitted by the first stars and black holes. Once established, these magnetic fields began to influence the formation of stars and galaxies. On a small scale, they helped regulate the collapse of gas clouds, guiding the flow of material and aiding in the birth of stars. Without magnetic fields, the process of star formation might have been far more disorganized and inefficient. On a larger scale, magnetic fields played a role in shaping the structure of galaxies, stabilizing their disks and influencing the behavior of interstellar gas. But the story doesn't end there. Magnetic fields also contributed to the cosmic web, the vast network of filaments and voids that make up the universe's large-scale structure. They acted like invisible threads, weaving through the fabric of space and interacting with dark matter and gas to guide the formation of galaxies and clusters. This intricate interplay helped create the complex and diverse universe we observe today. Despite their importance, the origins and evolution of cosmic magnetic fields remain shrouded in mystery. Detecting and measuring these fields in the early universe is a monumental challenge, as they leave only faint traces in the light and radiation we observe. However, advancements in technology and observational techniques, such as studying the polarization of the cosmic microwave background, are offering new insights into this cosmic puzzle. Understanding the role of magnetic fields in the early universe not only sheds light on the processes that shape the cosmos, but also deepens our appreciation for the invisible forces that continue to influence its evolution. As we move forward, we'll uncover more about how these magnetic fields helped lay the foundation for the universe's intricate tapestry. Next, we'll dive into another fascinating mystery that defined the early cosmos, so stay with us as we journey deeper into the unknown. As we unravel the mysteries of the early universe, one question stands out as both profound and tantalizing. Could life have emerged in the cosmos long before Earth even existed? This leads us to the mystery of the first life in the universe. While we often think of life as a relatively recent phenomenon, confined to planets like our own, the universe has been around for billions of years before Earth formed. Could life have taken root during those ancient times, and if so, where and how might it have begun? To explore this possibility, we need to consider the conditions required for life to emerge. Life, as we understand it, depends on certain key ingredients: liquid water, organic molecules, and a source of energy. In the early universe, these ingredients might have existed in surprising places. For example, some theories suggest that life could have emerged on planets orbiting the first generation of stars, known as population 3 stars. These stars, though short-lived, could have warmed nearby planets, providing the energy needed for chemical reactions to occur. Other possibilities include life arising in the dense gas clouds of early galaxies, or even on rogue planets drifting through the cold void of space. However, the early universe was a far harsher environment than today's cosmos. Radiation levels were higher, and the first stars and galaxies were bathed in intense ultraviolet light, which could have broken apart delicate organic molecules. Additionally, the elements necessary for life, like carbon and oxygen, were scarce in the early universe, having not yet been forged in the hearts of stars and scattered across the cosmos by supernova. This raises the question, could life have formed with a different chemistry, one not reliant on the elements we know today? Detecting ancient life, if it ever existed, presents even greater challenges. Unlike fossils on Earth, traces of life in the early universe would have been erased by billions of years of cosmic evolution. The first planets and potential habitats have long since been destroyed or transformed, leaving little evidence behind. Even if life did emerge, its remains would likely be buried beneath layers of stars, gas, and dust, making them nearly impossible to find. Yet astronomers are not entirely without hope. By studying the oldest galaxies and the faintest echoes of the early universe, they might uncover indirect clues about the conditions that could have supported life. For instance, the presence of water or organic molecules in ancient galaxies could hint at the possibility of life's emergence. Additionally, future telescopes designed to peer deeper into the cosmos might reveal new insights into the environments of the early universe and the potential for life to arise in such extreme conditions. The mystery of the first life in the universe invites us to think beyond the boundaries of our own planet and consider the vast possibilities of existence. If life did emerge in the early cosmos, it would reshape our understanding of what it means to be alive and the potential for life to thrive in even the most unlikely places. As we continue our journey through the mysteries of the early universe, let's ponder this profound question. Are we alone in the cosmos, or were we simply late to the story of life in the universe? Next, we'll delve into the formation of the first galaxies, uncovering how these ancient structures shaped the universe we see today. Now, turning our gaze to the vast structures that shaped the early universe, we encounter the mystery of the first galaxies. These ancient behemoths, born from the chaos of the cosmos, were the building blocks of the universe we see today. But how did they form, and what made them so different from the galaxies we observe now? The first galaxies emerged during a time known as the Cosmic Dawn, a period when the universe transitioned from darkness to light. Unlike modern galaxies, which are filled with heavy elements like carbon, oxygen, and iron, the first galaxies were composed almost entirely of hydrogen and helium, the simplest elements forged in the Big Bang. This meant that their stars, gas, and dust were fundamentally different from those in galaxies like our Milky Way. One of the key differences lies in their size and structure. The first galaxies were much smaller and more chaotic than their modern counterparts. They lacked the organized spiral arms or smooth elliptical shapes we see today. Instead, they were irregular and clumpy, with pockets of gas collapsing to form the first stars. These stars, known as population 3 stars, were massive and short-lived, exploding as supernova and seeding the universe with heavier elements over time. Another fascinating aspect of the first galaxies is their role in the cosmic web. These early structures were the seeds from which the large-scale structure of the universe grew. Gravity pulled them together, forming clusters and filaments that would eventually become the vast network of galaxies we observe today. Without these first galaxies, the universe as we know it would not exist. However, studying these ancient galaxies is no easy task. They are incredibly distant, and their light has traveled for billions of years to reach us. Astronomers rely on some of the most powerful telescopes ever built to catch glimpses of these faint, early structures. By observing them, scientists can piece together the story of how galaxies evolved and how they shaped the cosmos. The mystery of the first galaxies challenges us to rethink what we know about the universe's history. They remind us that our galaxy and everything within it is the product of processes that began billions of years ago. As we continue to explore the cosmos, each discovery brings us closer to understanding how these ancient structures laid the foundation for the universe we inhabit today. Next, we'll explore the mystery of the first supernova and their role in shaping the cosmos. Moving forward, let's turn our attention to the explosive events that fundamentally transformed the early universe, the first supernova. These colossal explosions were more than just spectacular cosmic fireworks. They were the universe's first factories for creating and distributing the heavy elements essential for everything from stars to planets to life itself. The first supernova occurred when the earliest stars, known as population 3 stars, reached the end of their short, fiery lives. These stars were unlike any we see today, massive, hot, and composed almost entirely of hydrogen and helium. When they exhausted their fuel, they collapsed under their own gravity and exploded in cataclysmic events that lit up the dark, early universe. These explosions were so powerful that they not only obliterated the stars themselves, but also sent shockwaves through the surrounding gas, triggering the birth of new stars and galaxies. One of the most significant contributions of these first supernovae was the creation of heavy elements. Inside the cores of population 3 stars, nuclear fusion fused hydrogen and helium into heavier elements like carbon, oxygen, and iron. When the stars exploded, these elements were scattered into space, enriching the surrounding gas. For the first time, the universe contained more than just hydrogen and helium. It now had the building blocks for complex chemistry. This process, known as nucleosynthesis, was crucial for shaping the cosmos. Without the heavy elements produced by supernova, the universe would have remained a barren, monotonous expanse of gas. Instead, these elements allowed for the formation of planets, the emergence of life, and the diversity of stars and galaxies we see today. The impact of these first supernova extended far beyond their immediate surroundings. The shock waves from these explosions compressed nearby gas, triggering the formation of the next generation of stars. Over time, this cycle of star formation, supernova, and enrichment helped shape the cosmic web, the large-scale structure of the universe. Despite their importance, studying these ancient supernovae is incredibly challenging. Their light has traveled for billions of years to reach us, and they are often obscured by dust and gas. However, astronomers use indirect methods, such as analyzing the chemical composition of ancient stars and galaxies, to piece together the story of these early explosions. The mystery of the first supernova is a testament to the interconnectedness of the cosmos. These explosions were not just destructive, they were creative, laying the groundwork for the universe's evolution. As we continue to explore the cosmos, each discovery brings us closer to understanding how these early events shaped the universe we inhabit today. Next, we'll delve into the mystery of the first black holes and their role in the early universe. Now, let's shift our gaze to one of the most enigmatic phenomena in the cosmos, the first black holes. These mysterious objects didn't just appear out of nowhere. Their formation and growth are deeply tied to the earliest chapters of the universe's history. Unlike the supermassive black holes we observe today, which lurk at the centers of galaxies, the first black holes were likely born from the collapse of the most massive population 3 stars. When these early stars reached the end of their lives, their cores collapsed under gravity, creating some of the first black holes in the universe. These primordial black holes were relatively small compared to their modern counterparts, but they played a significant role in shaping the cosmos. As they consumed nearby gas and dust, they grew in size and influence. Some even merged with other black holes, forming larger structures that would eventually become the seeds of supermassive black holes. Their immense gravitational pull helped gather and compress gas, triggering the formation of the first galaxies. In this way, black holes weren't just cosmic vacuums, they were architects of the universe's large-scale structure. Yet, studying these ancient black holes is no easy task. By the time their light reaches us, it has traveled for billions of years, making them incredibly faint and difficult to detect. Astronomers rely on indirect methods, such as observing the effects of their gravity on surrounding matter, or detecting the remnants of their activity in the form of quasars. These bright, energetic objects are thought to be powered by supermassive black holes feeding on vast amounts of material. One of the biggest challenges in understanding the first black holes is figuring out how they grew so quickly. Some theories suggest that they formed in dense regions of the early universe, where gas was plentiful and conditions were ideal for rapid growth. Others propose that they may have formed through direct collapse, skipping the star phase entirely and collapsing directly into black holes from massive clouds of gas. The mystery of the first black holes is a reminder of how much we still have to learn about the universe's origins. These objects not only shape the cosmos but also continue to influence its evolution. As we uncover more about their formation and growth, we gain deeper insights into the forces that shape the universe we see today. Next, we'll explore the formation of the first cosmic structures and how they evolved into the intricate cosmic web we observe now. Turning our attention to the cosmos' earliest building blocks, we arrive at the mystery of the first cosmic structures. These structures, including proto-galaxies and clusters, laid the foundation for everything we observe in the universe today. But how did these intricate networks of matter come to be? The answer lies in the delicate interplay between gravity, dark matter, and the faint ripples left over from the Big Bang. In the early universe, tiny fluctuations in density acted as seeds for the first cosmic structures. Areas with slightly more matter attracted more material through gravity, gradually growing denser and hotter. Over millions of years, these regions evolved into proto-galaxies, primordial versions of the galaxies we see today. Inside these proto-galaxies, gas and dust began to collapse, igniting the first stars and setting the stage for the universe's transformation from darkness to light. Dark matter played a crucial role in this process. Though invisible, its gravitational pull helped gather ordinary matter into clumps, accelerating the formation of these early structures. Without dark matter, the universe might have remained a diffuse sea of gas, never coalescing into galaxies and clusters. These clusters, in turn, became the nodes of an enormous cosmic web, an intricate tapestry of filaments and voids that stretches across the universe. The evolution of these structures was not a smooth or uniform process. As proto-galaxies merged and collided, they gave birth to larger, more complex galaxies. Supermassive black holes, born in the hearts of these galaxies, further shaped their growth by releasing immense amounts of energy that pushed gas outward, regulating star formation. Over billions of years, this chaotic dance of gravity, fusion, and feedback sculpted the cosmos into its present form. Today, astronomers study these ancient structures using powerful telescopes and simulations. By observing distant galaxies and mapping the cosmic web, they piece together the story of how the universe grew from its humble beginnings into the vast, interconnected network we see now. Yet, many questions remain. What triggered the initial density fluctuations? How exactly did dark matter guide the assembly of these structures? And what role did the first stars and black holes play in shaping their evolution? The mystery of the first cosmic structures is a testament to the universe's remarkable ability to organize itself from chaos. As we uncover more about these primordial building blocks, we gain a deeper understanding of how the cosmos evolved and our place within it. Next, we'll delve into the mystery of the first light elements and their role in the universe's chemistry. Moving from the grand structures of the early universe, let's zoom in on the very essence of creation, the first light elements. Hydrogen and helium, the simplest and most abundant elements, were the building blocks of everything that followed. But how did these elements come into existence, and what role did they play in shaping the cosmos as we know it? In the first few minutes after the Big Bang, the universe was a seething, dense soup of particles. As it expanded and cooled, protons and neutrons began to combine, forming the nuclei of light elements through a process called Big Bang nucleosynthesis. Almost all the hydrogen in the universe today originated during this brief window, alongside a significant amount of helium. These elements were the first steps in the universe's chemical evolution, setting the stage for the formation of stars, galaxies, and eventually life itself. But why were hydrogen and helium so dominant? It all comes down to the conditions of the early universe. The temperatures and pressures were just right for these elements to form, but not heavy enough to create anything more complex. Elements like carbon and oxygen would come later, forged in the hearts of stars. Hydrogen, being the simplest element with just one proton, became the primary fuel for the first stars. As these stars ignited, they fused hydrogen into helium, releasing energy that lit up the cosmos. This process not only illuminated the universe, but also began the gradual enrichment of space with heavier elements, paving the way for the complex chemistry we see today. Helium, though less abundant than hydrogen, played a crucial role in cooling the early universe. As gas clouds collapsed to form stars, helium acted as a coolant, allowing the gas to condense more efficiently. This cooling effect was essential for the formation of the first stars and galaxies, making helium a key player in cosmic evolution. Today, we can trace the presence of these primordial elements in the oldest stars and distant galaxies. Their abundance provides a window into the universe's earliest moments, helping us piece together the story of how it all began. Yet, questions remain. Why did the early universe produce such precise amounts of hydrogen and helium? And how did these elements influence the formation of the first stars and galaxies? The mystery of the first light elements is a reminder of the universe's simplicity at its birth, a simplicity that gave rise to the complexity we see today. As we continue to explore these primordial building blocks, we uncover not just the history of the cosmos, but also the origins of the elements that make up everything, including ourselves. Next, we'll explore the mystery of the first cosmic rays and their impact on the early universe. Now, let's turn our attention to another fascinating puzzle of the early universe, the mystery of the first cosmic rays. These high-energy particles, traveling at nearly the speed of light, have been zipping through the cosmos since the dawn of time. But where did they come from, and how have they shaped the universe we see today? Cosmic rays are made up of protons, atomic nuclei, and other subatomic particles carrying immense energy. While we detect them constantly bombarding Earth's atmosphere, their origins in the early universe remain a subject of intense study. Some scientists believe the first cosmic rays were produced by the violent deaths of massive stars, known as supernovae. Others suggest they may have originated from exotic objects like quasars or even the decay of dark matter particles. In the early universe, these cosmic rays played a crucial role in shaping the cosmic landscape. They helped ionize the hydrogen gas that filled space, contributing to the epoch of reionization, the period when the first stars and galaxies began to light up the cosmos. By ionizing gas, cosmic rays may have influenced the formation of stars and galaxies, acting as a kind of cosmic fertilizer for the structures we see today. Detecting and studying these ancient cosmic rays, however, is no easy task because they're so energetic they're difficult to trace back to their sources. Scientists use a variety of methods, from ground-based observatories to space telescopes, to study their properties and origins. One of the most famous experiments, the Pierre Auger Observatory in Argentina, has been instrumental in detecting ultra-high-energy cosmic rays and providing clues about their cosmic journey. Yet many questions remain. What exactly powered the first cosmic rays to such incredible speeds? How did they interact with the early universe's matter and radiation? And what can they tell us about the conditions of the cosmos in its infancy? The mystery of the first cosmic rays is a testament to the universe's complexity and dynamism. These particles, born in the chaos of the early cosmos, continue to travel across vast distances, carrying with them secrets of the universe's origins. As we unravel their story, we gain deeper insights into the forces that shape the cosmos and the incredible journey of energy and matter from the Big Bang to the present day. Next, we'll delve into the mystery of the first cosmic dust and its role in the early universe. Now, let's shift our focus to another intriguing piece of the cosmic puzzle, the mystery of the first cosmic dust. This fine, grainy material, often referred to as the building blocks of the universe, played a vital role in shaping the cosmos as we know it. But how did it form, and what part did it play in the creation of stars and planets? Cosmic dust, made up of tiny particles of carbon, silicon, and other elements, began to appear in the early universe as the first stars reached the end of their lives. When these massive stars exploded in spectacular supernovae, they scattered their innards across space, seeding the cosmos with the raw materials for future generations of stars and planets. This dust, though seemingly insignificant, became a key ingredient in the cosmic recipe for life. In the early universe, cosmic dust acted as a catalyst for star formation. Dust particles provided surfaces for gas molecules to cling to, allowing them to cool and collapse under gravity. This process gave birth to new stars, which in turn produced even more dust, creating a cycle of creation and recycling that continues to this day. Without these tiny particles, the universe might have remained a vast, empty expanse of gas. But cosmic dust didn't just contribute to star formation, it also played a crucial role in the birth of planets. As stars formed, dust grains began to clump together, forming larger and larger structures. Over time, these clumps grew into planets, asteroids, and other celestial bodies. In a very real sense, every planet, including Earth, owes its existence to cosmic dust. Studying the first cosmic dust, however, is no simple task. Because it formed so long ago, much of it has been recycled or destroyed. But scientists have found ways to peer into the past. By observing distant galaxies and analyzing the light that passes through cosmic dust clouds, researchers can piece together clues about its origins and evolution. One of the most fascinating discoveries is that cosmic dust could have also played a role in the chemistry of the early universe. Some scientists believe that these tiny particles may have provided the surfaces for the first complex molecules to form, potentially laying the groundwork for the emergence of life. The mystery of the first cosmic dust reminds us that even the smallest things can have an enormous impact. These minuscule particles, born from the ashes of ancient stars, shaped the universe in ways we're only beginning to understand. As we continue to explore their story, we uncover new insights into the origins of stars, planets, and perhaps even life itself. Next, we'll explore the role of cosmic winds in the early universe and how they helped shape the cosmos. Let's now turn our attention to the powerful force of cosmic winds and their role in the early universe. These winds, streams of charged particles propelled by the energy of stars and supernova, acted as cosmic sculptors, shaping galaxies and spreading elements across the vast expanse of space. In the early universe, as stars formed and exploded, they unleashed tremendous amounts of energy into their surroundings. This energy drove streams of particles outward at incredible speeds, creating cosmic winds. These winds carried with them not just energy, but also heavy elements forged in the hearts of stars, dispersing them into the interstellar medium. This process was crucial for enriching the universe with the materials needed to form new stars, planets, and eventually life. One of the most significant roles of cosmic winds was in shaping the structure of galaxies. As these winds swept through regions of space, they pushed gas and dust, influencing where new stars could form. In some cases, cosmic winds even halted star formation entirely by blowing away the raw materials needed. This interplay between creation and destruction helped determine the size, shape, and evolution of galaxies in the early universe. Cosmic winds also played a key role in distributing elements across the cosmos. Before these winds, heavy elements like carbon, oxygen, and iron were confined to the regions around the stars that created them. But as winds carried these elements outward, they mixed with the surrounding gas, seeding other regions with the building blocks of planets and life. Without this process, the universe might have remained a patchwork of isolated chemical islands, each lacking the diversity needed for complexity. Studying cosmic winds is challenging as they leave behind subtle clues rather than direct evidence. However, astronomers have developed innovative methods to observe their effects. By analyzing the light from distant galaxies and the absorption patterns of gas clouds, researchers can trace the paths of ancient winds and understand their impact on the cosmos. The mystery of the first cosmic winds reminds us of the interconnectedness of the universe. These invisible streams of particles, born from the depths of stars, played a vital role in shaping the cosmos and spreading the elements necessary for life. As we continue to unravel their story, we gain deeper insights into the forces that sculpted the early universe. Next, we'll explore the first cosmic explosions and how they shaped the universe we see today. Moving forward in our cosmic journey, we now encounter the dramatic and awe-inspiring phenomenon of the first cosmic explosions. These colossal events, such as gamma-ray bursts, were like the universe's fireworks, lighting up the darkness of the early cosmos and leaving lasting imprints on its evolution. Gamma-ray bursts are some of the most energetic events ever observed, releasing more energy in seconds than our Sun will emit in its entire lifetime. In the early universe, these bursts were likely triggered by the collapse of massive stars or the collision of neutron stars. Their intense flashes of gamma rays, the most energetic form of light, traveled vast distances, illuminating regions of space that were otherwise shrouded in darkness. These bursts not only provided light but also acted as cosmic beacons, helping astronomers map the early universe. The impact of these explosions was profound. When a gamma-ray burst occurred, it unleashed a torrent of high-energy radiation and particles into its surroundings. This energy could ionize nearby gas, stripping electrons from atoms and altering the chemical composition of the interstellar medium. In some cases, these bursts may have even triggered star formation by compressing gas clouds, while in others, they could have destroyed potential star-forming regions by dispersing the necessary materials. Another critical role of these early explosions was the dispersal of heavy elements. Just like cosmic winds, gamma-ray bursts helped spread elements like carbon, oxygen, and iron across the universe. These elements, forged in the hearts of stars, were ejected into space during the explosions, enriching the cosmic environment. This process was essential for the formation of planets and the eventual emergence of life. Studying these ancient explosions is no easy task. Gamma-ray bursts are fleeting, lasting only seconds to minutes, but their afterglows can linger for days, weeks, or even months. By observing these afterglows, astronomers can piece together the story of the bursts, their origins, and their effects on the surrounding universe. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have been instrumental in detecting and analyzing these distant events. The mystery of the first cosmic explosions reminds us of the dynamic and violent nature of the early universe. These titanic events shaped the cosmos in ways we are only beginning to understand, influencing star formation, chemical enrichment, and the large-scale structure of the universe. As we continue to explore their story, we uncover more about the forces that forged the universe we inhabit today. Next, we'll delve into the enigmatic origins of the first cosmic magnetic fields and their role in shaping the cosmos. Now, let's turn our attention to another fascinating puzzle of the early universe, the mystery of the first cosmic magnetic fields. These invisible forces, though often overlooked, played a crucial role in shaping the cosmos as we know it today. But where did these magnetic fields come from, and how did they influence the birth of stars and galaxies? Cosmic magnetic fields are thought to have originated in the turbulent conditions of the early universe. One leading theory suggests they were born from tiny fluctuations in the primordial plasma, the hot, dense soup of particles that filled the cosmos after the Big Bang. As this plasma expanded and cooled, these fluctuations could have generated weak magnetic fields. Over time, these fields may have been amplified by the motion of charged particles, creating the cosmic magnetic fields we observe today. The role of these magnetic fields in star and galaxy formation cannot be overstated. Magnetic fields influence the movement of gas and dust, the building blocks of stars. They can channel the flow of material, guiding it into dense clumps that eventually collapse under gravity to form stars. Without these fields, the process of star formation might have been far less efficient, altering the timeline and structure of the universe's evolution. Magnetic fields also play a key part in galaxy formation. As gas and dust gathered to form galaxies, magnetic fields helped regulate the dynamics of these swirling masses. They could stabilize rotating disks, prevent the fragmentation of gas clouds, and even drive the powerful jets of material often seen shooting from the centers of galaxies. These effects shaped the large-scale structure of the universe, influencing how galaxies formed and evolved over billions of years. Yet, studying these ancient magnetic fields is no simple task. Unlike stars or galaxies, magnetic fields are invisible and can only be detected indirectly. Astronomers rely on observations of polarized light, the alignment of light waves, to trace the presence and strength of these fields. Instruments like radio telescopes and space observatories have provided valuable data, but much about the origin and early history of cosmic magnetic fields remains shrouded in mystery. What we do know is that these fields are a fundamental part of the cosmic fabric. They connect stars, galaxies, and even the vast voids of space, weaving an intricate web of forces that continue to shape the universe. As we uncover more about these invisible threads, we gain a deeper understanding of the processes that forged the cosmos billions of years ago. Next, we'll explore the formation of the first cosmic particles and their role in the unfolding story of the universe. Turning our gaze to the building blocks of the cosmos, we uncover the mystery of the first cosmic particles. These fundamental particles, born in the fiery aftermath of the Big Bang, laid the groundwork for everything we see around us today. But how did these particles come into existence, and what role did they play in shaping the early universe? In the earliest moments of the cosmos, the universe was unimaginably hot and dense, filled with a seething plasma of particles and energy. As the universe expanded and cooled, the first particles began to form. Among these were quarks and gluons, the building blocks of protons and neutrons. Over time, as the universe continued to cool, these quarks and gluons combined to form protons and neutrons, which later fused to create the first atomic nuclei. This process, known as nucleosynthesis, marked the beginning of the chemical elements that make up our universe. These early particles played a pivotal role in cosmic evolution. Protons and neutrons formed the nuclei of the first atoms, primarily hydrogen and helium, which became the raw materials for stars and galaxies. Without these particles, the universe would have remained a vast, empty void, devoid of structure. Their formation set the stage for the next great chapter in cosmic history, the birth of the first stars. Detecting these ancient particles, however, is no easy feat. Scientists rely on a combination of theoretical models and observations to piece together their story. One key method involves studying the cosmic microwave background, the afterglow of the Big Bang, which carries imprints of the early universe's conditions. High-energy particle accelerators, like the Large Hadron Collider, also play a crucial role by recreating the extreme conditions of the early universe, allowing researchers to observe how particles behave and interact. The first cosmic particles are more than just relics of the past. They are the foundation of the universe as we know it. By understanding their origins and behavior, we gain deeper insights into the forces that shaped the cosmos billions of years ago. Next, we'll journey into the era of the first cosmic waves and their profound impact on the universe's evolution. Shifting our focus to the ripples that shape the cosmos, we encounter the mystery of the first cosmic waves. Among these, gravitational waves stand out as one of the most fascinating phenomena. These waves, first predicted by Albert Einstein, are disturbances in the fabric of spacetime itself, caused by the movement of massive objects. But what role did they play in the early universe, and how did they influence its evolution? In the moments following the Big Bang, the universe was a turbulent place filled with intense energy and rapid changes. It was during this time that the first gravitational waves likely emerged, created by violent events like the collisions of primordial black holes or the rapid expansion of spacetime during cosmic inflation. These waves carried information about the universe's earliest moments, encoding details about its structure and the forces at play. Gravitational waves are more than just echoes of the past. They are a window into the universe's infancy. Unlike light, which can be absorbed or scattered, gravitational waves travel unimpeded through the cosmos, providing a pristine record of events that occurred billions of years ago. By studying these waves, scientists can uncover secrets about the universe's birth and its subsequent growth. One of the most significant breakthroughs came in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, directly detected gravitational waves for the first time, confirming their existence and opening a new era of astronomy. The impact of these early waves on cosmic evolution was profound. They influenced the distribution of matter, helping to shape the large-scale structure of the universe. As these waves propagated through the cosmos, they left subtle imprints on the cosmic microwave background, the afterglow of the Big Bang. These imprints provide clues about the conditions of the early universe and the processes that led to the formation of galaxies and stars. Today, scientists continue to hunt for these ancient ripples, using advanced detectors and space-based observatories like the planned Laser Interferometer Space Antenna, or LISA. By capturing more gravitational wave signals, researchers hope to piece together a more complete picture of the universe's origins and evolution. The first cosmic waves are a testament to the dynamic and interconnected nature of the cosmos. They remind us that the universe is not static but constantly in motion, shaped by the events of its past. As we delve deeper into their mysteries, we uncover new insights into the forces that have guided the cosmos from its birth to the present day. Next, we'll explore the formation of the first cosmic structures and their role in the universe's grand design. Turning our attention to the building blocks of the cosmos, we delve into the mystery of the first cosmic structures. In the early universe, the distribution of matter was not uniform. Tiny fluctuations in density, amplified by gravity, began to pull matter together, giving rise to the seeds of the first structures. These structures, known as protogalaxies, were the precursors to the galaxies we observe today. Protogalaxies formed within the cosmic web, the vast network of filaments and voids shaped by dark matter and gravity. As these structures grew, they began to attract more gas and dust, eventually collapsing under their own gravity to form stars and, later, entire galaxies. This process was not immediate. It took hundreds of millions of years for these structures to mature and stabilize. The evolution of these early structures was shaped by a variety of forces. Dark matter played a crucial role, providing the gravitational scaffolding that allowed galaxies to form. Meanwhile, the first stars and supernova enriched the surrounding gas with heavy elements, enabling the formation of more complex systems. Over time, these protogalaxies merged and interacted, growing into the diverse range of galaxies we see in the universe today. One of the most intriguing aspects of these early structures is their relationship to the cosmic microwave background, or CMB. The CMB contains subtle imprints of the density fluctuations that gave rise to protogalaxies, offering a snapshot of the universe just 380,000 years after the Big Bang. By studying these imprints, scientists can trace the origins of cosmic structures and understand how they evolved over billions of years. Today, telescopes like the Hubble and the James Webb Space Telescope allow us to peer back in time, observing galaxies in their infancy. These observations reveal a universe in flux where young galaxies are smaller, more chaotic, and often in the process of merging. Through these discoveries, we gain a deeper understanding of how the first cosmic structures shaped the universe into the intricate and beautiful tapestry we see today. The formation of the first cosmic structures marks a pivotal chapter in the universe's history. It was during this time that the seeds of galaxies, stars, and planets were sown, setting the stage for the rich diversity of the cosmos. As we continue to explore these ancient formations, we uncover the profound connections between the universe's past and its present. Next, we'll examine the origin of the first cosmic light and its role in illuminating the early universe. Now, let's step into the era when the universe first began to shine. the mystery of the first cosmic light takes us to a time when darkness gave way to illumination, forever changing the fabric of the cosmos. After the universe cooled following the Big Bang, it was plunged into what's known as the cosmic dark ages, a period devoid of stars or galaxies. But this darkness didn't last forever. The first cosmic light emerged as the universe's first stars ignited, ending the dark ages and beginning the epoch of reionization. These stars, known as population 3 stars, were unlike any we see today. They were massive, hot, and short-lived, burning through their fuel in mere millions of years. Their intense ultraviolet radiation ionized the surrounding hydrogen gas, transforming the universe from opaque to transparent. This momentous transition allowed light to travel freely through space, marking the dawn of the cosmic light we observe today. The role of this first light in cosmic evolution cannot be overstated. It not only ended the Dark Ages but also set the stage for the formation of galaxies and the large-scale structure of the universe. The energy from these early stars helped shape the growth of protogalaxies, driving the collapse of gas clouds and triggering the birth of new stars. Additionally, the first cosmic light seeded the universe with heavy elements, forged in the cores of these massive stars and scattered by their explosive deaths. Detecting this ancient light is one of the greatest challenges in modern astronomy. While the first stars themselves are too distant and faint to observe directly, their collective impact can be studied through the cosmic microwave background, or CMB. The CMB carries faint echoes of this early light, revealing subtle patterns left by the first stars and the process of reionization. Cutting-edge telescopes like the James Webb Space Telescope are now peering deep into the universe's past, searching for the earliest galaxies and the remnants of those first stars. By analyzing the light from these distant objects, scientists hope to unravel the mysteries of the first cosmic light and its role in shaping the universe as we know it. The first cosmic light was not just a moment of illumination, it was a turning point in the history of the cosmos. It paved the way for the formation of stars, galaxies, and ultimately the complex structures that define our universe today. As we continue to explore this pivotal era, we gain a deeper understanding of how light transformed the universe from darkness into the vibrant expanse we now observe. Up next, we'll explore the formation of the first cosmic elements, the building blocks that laid the foundation for everything that followed. Now, let's turn our attention to the very ingredients that set the stage for the universe's grand evolution. The mystery of the first cosmic elements begins just moments after the Big Bang, when the cosmos was a seething cauldron of energy and particles. As the universe expanded and cooled, the first light elements began to form, laying the foundation for everything we see today. During the first few minutes of the universe's existence, a process called nucleosynthesis took place. This is when protons and neutrons combine to form the nuclei of the simplest elements: hydrogen, helium, and trace amounts of lithium. Hydrogen, the most abundant element, made up about 75% of the universe's matter, while helium accounted for nearly 25%. These elements became the raw materials for the first stars and galaxies, setting the stage for the cosmic structures we observe today. The significance of these first elements cannot be overstated. Hydrogen and helium formed the vast clouds of gas that eventually collapsed under gravity to ignite the first stars. These stars, in turn, fused these light elements into heavier ones like carbon, oxygen, and nitrogen in their cores. When these early stars exploded as supernova, they scattered these heavier elements across the cosmos, enriching the universe with the building blocks of planets, life, and everything in between. Detecting these primordial elements is a monumental challenge, but scientists have made remarkable progress. By studying the spectra of the oldest stars and the cosmic microwave background, researchers can trace the composition of the early universe. The cosmic microwave background, in particular, carries the faint imprints of these first elements, offering a snapshot of the universe just moments after its birth. Additionally, observations of distant quasars reveal absorption lines in their light, providing clues about the distribution of hydrogen and helium in the early cosmos. The first cosmic elements were more than just the ingredients of stars and galaxies. They were the seeds of complexity in the universe. Without them, the cosmos would have remained a featureless expanse of hydrogen and helium. Their formation marked the beginning of a cosmic journey that led to the intricate and diverse universe we inhabit today. As we continue to study these ancient elements, we gain a deeper appreciation for their role in shaping the universe. They remind us that even the simplest building blocks can give rise to the most extraordinary structures, a testament to the remarkable story of cosmic evolution. Coming up next, we'll delve into the formation of the first cosmic particles, exploring how these tiny specks of matter influenced the early universe. Building on the foundation of the first cosmic elements, let's now shift our focus to the tiny but mighty specks of matter that emerged in the early universe, the first cosmic particles. These particles, though minuscule, played a pivotal role in shaping the cosmos as we know it. In the chaotic aftermath of the Big Bang, the universe was a dense, seething soup of energy and fundamental particles. Quarks and gluons, the building blocks of protons and neutrons, swirled in a hot, primordial plasma. As the universe expanded and cooled, these particles began to combine, forming protons and neutrons. This marked the birth of the first stable atomic nuclei, a crucial step in the universe's evolution. But protons and neutrons were just the beginning. The early universe was also teeming with other elementary particles, such as electrons, neutrinos, and photons. These particles interacted in complex ways, governed by the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. For instance, photons, particles of light, dominated the early universe, scattering off charged particles and creating a glowing fog that persisted for hundreds of thousands of years. The role of these first cosmic particles was immense. Protons and neutrons formed the nuclei of hydrogen and helium, the first elements that we discussed earlier. Electrons, once captured by these nuclei, created the first atoms, allowing light to travel freely and ending the cosmic dark ages. Neutrinos, often called ghost particles because of their elusive nature, influenced the growth of cosmic structures by subtly shaping the distribution of matter. Detecting these early particles is no easy task, but scientists have devised ingenious methods to study them. For example, the cosmic microwave background radiation provides a snapshot of the universe when it was just 380,000 years old, revealing the imprints of these particles. Neutrino detectors buried deep underground capture the faint signals of these ghostly particles, offering clues about their role in the early universe. The story of the first cosmic particles is a testament to how even the smallest components can have profound impacts. They laid the groundwork for the formation of stars, galaxies, and ultimately the complex structures we see today. As we continue to unravel the mysteries of these early particles, we gain a deeper understanding of the universe's infancy. Next, we'll explore the origins of the first cosmic waves, another fascinating chapter in the story of the early universe. Moving forward in our cosmic journey, let's turn our attention to the first cosmic waves, ripples that traveled through the fabric of space-time itself. Among these, gravitational waves stand out as one of the most intriguing phenomena, offering a unique window into the universe's earliest moments. Gravitational waves are disturbances in space-time caused by massive, accelerating objects, such as colliding black holes or neutron stars. While we've only recently detected these waves using advanced observatories like LIGO and Virgo, theorists believe they originated much earlier during the universe's infancy. In fact, the first cosmic waves likely emerged just moments after the Big Bang, when the universe was a turbulent sea of energy and matter. these primordial waves would have been generated by violent events such as phase transitions in the early universe or the rapid inflation of spacetime itself. As the universe expanded, these waves stretched and rippled across the cosmos, carrying with them information about the conditions of the early universe. Imagine them as echoes of the universe's birth, faint whispers that have traveled billions of years to reach us. But why are these waves so important? For one, they provide a completely new way to study the early universe, complementing what we've learned from light and particles. While the cosmic microwave background radiation gives us a snapshot of the universe at around 380,000 years old, gravitational waves could potentially reveal what happened even earlier, during the first fractions of a second after the Big Bang. The impact of these waves extends beyond just observation. They likely played a role in shaping the large-scale structure of the universe. By influencing the distribution of matter, gravitational waves may have contributed to the formation of galaxies and clusters, leaving their imprint on the cosmic web we see today. Detecting these ancient waves, however, is a monumental challenge. The signals from the early universe are incredibly faint, buried beneath the noise of more recent events. Scientists are now developing next-generation detectors, such as space-based observatories like LISA, to hunt for these elusive ripples. If successful, these missions could unlock secrets about the universe's origins that were previously thought to be beyond our reach. The study of the first cosmic waves is a reminder that the universe speaks to us in many ways through light, particles, and now, the subtle tremors of spacetime. As we continue to tune into these cosmic whispers, we edge closer to understanding how it all began. Up next, we'll delve into the formation of the first cosmic structures, a key milestone in the universe's evolution. Now, let's shift our focus to the very building blocks of the cosmos, the first cosmic structures. These structures, like proto-galaxies and clusters, mark a critical turning point in the universe's evolution, laying the foundation for the vast, intricate web of galaxies we observe today. The story of these structures begins in the aftermath of the Big Bang, when the universe was a dense, hot soup of particles and energy. As the cosmos expanded and cooled, tiny fluctuations in density ripples left over from the Big Bang began to grow. These fluctuations were the seeds of the first cosmic structures, acting as gravitational traps that pulled in matter over time. At first, these structures were small and simple, with regions of slightly higher density gradually accumulating gas and dark matter. Over hundreds of millions of years, these clumps grew larger and more complex, eventually forming protogalaxies, the precursors to modern galaxies. These protogalaxies were not the majestic spirals or ellipticals we see today, but rather chaotic, turbulent clouds of gas and stars in the process of finding their shape. As protogalaxies formed, they began to cluster together, pulled by the immense gravitational forces of dark matter. These clusters became the nodes of the cosmic web, connected by vast filaments of gas and dark matter. Within these clusters, galaxies interacted, collided, and merged, shaping the diverse array of galaxies we see in the universe today. The evolution of these structures was not a linear process. It was shaped by a variety of factors, including the cooling of gas, the formation of stars, and the feedback from supernova and black holes. These processes enriched the universe with heavy elements, allowing for the formation of planets and eventually life. Studying the first cosmic structures is no easy task because they formed so long ago. Their light has traveled billions of years to reach us, making them incredibly faint. Astronomers rely on powerful telescopes and simulations to piece together their history. By observing distant galaxies and mapping the large-scale structure of the universe, we can trace the evolution of these early structures and understand how they shaped the cosmos. The first cosmic structures are more than just a chapter in the universe's history. They are the foundation of everything we see today. From the grandest galaxy clusters to the smallest stars, their origins trace back to those early fluctuations in the infant universe. As we continue to explore these structures, we uncover not just the story of the universe's past, but also the blueprint for its future. Up next, we'll journey into the era of the first cosmic light, when the universe transitioned from darkness to illumination, forever changing the cosmic landscape. Now, let's step into the era when the universe first lit up, a transformative moment that forever changed the cosmic landscape. The mystery of the first cosmic light takes us back to a time when the universe was shrouded in darkness, filled with neutral hydrogen gas that absorbed any light attempting to pass through. But then, something extraordinary happened. The first stars and galaxies ignited, flooding the cosmos with light and ionizing the surrounding gas. This epoch, known as the era of reionization, marked the universe's transition from a dark, opaque state to one filled with luminous objects we can observe today. The first cosmic light didn't just illuminate the universe, it played a critical role in shaping its evolution. As the first stars burst into existence, their intense ultraviolet radiation began to ionize the hydrogen gas around them, stripping electrons from atoms and creating a transparent universe. Over time, this process spread across vast regions, carving out bubbles of ionized gas that eventually overlapped, completing the epoch of reionization. This light also carried with it the seeds of structure, influencing the formation of galaxies and the large-scale web of the cosmos. Detecting this ancient light, however, is no simple task. It's incredibly faint, having traveled billions of years to reach us, and its origins lie at the very edge of what our telescopes can observe. Astronomers rely on some of the most powerful observatories, like the James Webb Space Telescope, to peer into this distant past. By studying the light from the earliest galaxies and quasars, we can piece together the story of how the universe transitioned from darkness to light. These observations also reveal clues about the nature of the first stars and galaxies, helping us understand their role in reionizing the cosmos. The first cosmic light is more than just a scientific curiosity, it's a window into the universe's formative years. By unraveling its mysteries, we gain insight into the processes that shaped the cosmos and laid the groundwork for the universe we inhabit today. Up next, we'll delve into the formation of the first cosmic elements, the building blocks of stars, planets, and life itself. Turning our attention to the very building blocks of the cosmos, we now explore the mystery of the first cosmic elements. In the early universe, before stars and galaxies existed, the cosmos was a sea of simplicity, composed primarily of hydrogen and helium, the first elements forged in the aftermath of the Big Bang. These elements didn't just fill the universe, they laid the foundation for everything that followed, from the first stars to the planets and life itself. But how did these elements form, and what role did they play in shaping the universe we see today? The story begins just moments after the Big Bang, during a period known as Big Bang nucleosynthesis. In the intense heat and density of the newborn universe, protons and neutrons combine to form the simplest atomic nuclei: hydrogen, helium, and trace amounts of lithium. This process lasted only a few minutes, but it set the stage for the cosmic chemistry to come. These primordial elements became the raw material for the first stars, which would later forge heavier elements in their cores through nuclear fusion. When the first stars ignited, they didn't just light up the universe, they transformed it. Inside their blazing hearts, hydrogen and helium fused to create heavier elements like carbon, oxygen, and nitrogen. When these massive stars died in spectacular supernova explosions, they scattered these newly formed elements across the cosmos. This enrichment process continued with each generation of stars, gradually building the complex chemistry needed for planets and eventually life. The first cosmic elements, therefore, weren't just inert matter, they were the seeds of complexity that allowed the universe to evolve. Detecting these ancient elements is a challenge, but modern astronomy has given us the tools to uncover their origins. By studying the light from distant quasars and the spectra of ancient stars, astronomers can trace the abundance of elements in the early universe. Telescopes like the James Webb Space Telescope allow us to peer back in time, observing the chemical fingerprints of the first stars and galaxies. These observations help us piece together the story of how the universe's first elements formed and how they shaped its evolution. The mystery of the first cosmic elements is more than just a scientific puzzle, it's a journey to the very origins of the universe's complexity. By understanding how these elements formed and spread, we gain insight into the processes that made the cosmos rich and diverse. And with that, we'll now shift our focus to the role of the first cosmic particles, the tiny yet influential players that shaped the universe in ways we're just beginning to understand. Now, let's dive into the enigmatic world of the very first cosmic particles. In the early universe, even before the first stars and galaxies began to shine, the cosmos was teeming with tiny particles that played a crucial role in shaping its evolution. These particles, often invisible and elusive, were the fundamental building blocks that set the stage for everything we see today. But what were they and how did they come into existence? The story of the first cosmic particles begins just moments after the Big Bang. In the searing heat and density of the newborn universe, particles like quarks, electrons, and neutrinos swarmed together in a chaotic frenzy. As the universe expanded and cooled, quarks combined to form protons and neutrons, the essential components of atomic nuclei. These particles didn't just exist in isolation. They interacted with one another through the fundamental forces of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces. These interactions were the first steps in the universe's journey toward complexity. Among these particles, neutrinos, often called ghost particles, were particularly fascinating. Unlike other particles, neutrinos interact very weakly with matter, making them incredibly difficult to detect. Yet, they played a vital role in the early universe, influencing everything from the formation of the first atoms to the large-scale structure of the cosmos. As the universe continued to cool, protons and neutrons began to combine, forming the first atomic nuclei during a process known as Big Bang nucleosynthesis. This period laid the groundwork for the creation of hydrogen and helium, the universe's first elements. Detecting these ancient particles is no easy task, but modern science has developed ingenious methods to uncover their secrets. Neutrino detectors, like those buried deep underground, capture these elusive particles as they travel through the Earth. Meanwhile, experiments at particle accelerators, such as the Large Hadron Collider, recreate the extreme conditions of the early universe, allowing scientists to study how these particles behaved in the cosmos' infancy. By piecing together these clues, researchers are slowly unraveling the story of the first cosmic particles and their role in shaping the universe. The mystery of the first cosmic particles isn't just about understanding the past, it's about uncovering the fundamental rules that govern the universe. These tiny particles, though often overlooked, were the architects of cosmic evolution, influencing everything from the formation of atoms to the structure of galaxies. As we continue to explore their origins, we gain deeper insights into the very fabric of existence, bringing us closer to understanding the universe's most profound mysteries. Shifting our focus to the realm of cosmic waves, we uncover another profound mystery of the early universe, the first cosmic waves, including gravitational waves. These ripples in the fabric of space-time are not just fascinating phenomena, they are key to understanding how the universe evolved in its earliest moments. Gravitational waves are disturbances caused by massive cosmic events, like the collision of black holes or neutron stars, but their origins trace back to the universe's infancy, when extreme conditions generated waves that still echo through the cosmos today. The first cosmic waves are believed to have formed during the universe's initial moments, when rapid inflation and violent particle interactions created fluctuations in spacetime. These early waves carried energy and information across the universe, influencing the distribution of matter and the formation of cosmic structures. Unlike light, gravitational waves can travel through dense regions of the universe without being absorbed or scattered, making them a unique tool for probing the earliest epochs of cosmic history. Understanding these waves is like listening to the whispers of the universe's birth. By studying them, scientists can gain insights into events that occurred long before the first stars and galaxies formed. For instance, the detection of primordial gravitational waves could provide direct evidence of cosmic inflation, the period of rapid expansion that occurred just after the Big Bang. Such discoveries would not only confirm key theories about the universe's origins, but also shed light on the fundamental forces and particles that governed its evolution. Modern observatories like the Laser Interferometer Gravitational Wave Observatory, or LIGO, have already detected gravitational waves from recent cosmic events. However, the hunt for the first cosmic waves remains a significant challenge. These primordial waves are incredibly weak, requiring highly sensitive instruments and advanced techniques to detect. Efforts to observe them are ongoing, with projects like the Cosmic Microwave Background experiments aiming to uncover subtle imprints left by these ancient waves. The mystery of the first cosmic waves is not just about unraveling the past, it's about deepening our understanding of the universe's fundamental laws. These waves offer a unique window into the cosmos' earliest moments, revealing how the universe transitioned from a hot, dense state to the vast, complex structure we see today. As we continue to explore their origins, we move closer to answering some of the most profound questions about the universe's birth and evolution. With each discovery, we gain a clearer picture of the cosmic tapestry woven by the first waves that ever rippled through space-time. As we reach the end of our journey through the 50 mysteries of the early universe, it's clear that these questions are more than just scientific puzzles, they are windows into the very fabric of existence. From the enigma of the Big Bang singularity to the elusive nature of dark energy, each mystery challenges our understanding of reality and pushes the boundaries of human knowledge. These unanswered questions remind us that the universe is far more complex and wondrous than we can currently comprehend. The early universe was a place of extremes and transformations, where fundamental forces and particles shaped the cosmos we see today. Yet, so much of that era remains shrouded in mystery. What sparked the Big Bang? What is the true nature of dark matter and dark energy? How did the first stars and galaxies form? These mysteries are not just academic, they are invitations to explore, to wonder, and to imagine the unseen forces that govern our universe. As we continue to unravel these cosmic secrets, we are also reminded of how much we have yet to discover. Every new observation, every breakthrough brings us closer to understanding the universe's origins, but it also opens new doors to even greater questions. The mysteries of the early universe are a testament to the endless curiosity that drives humanity forward. So, as we conclude this exploration, I invite you to keep pondering these questions. What do you think lies beyond our current understanding? How do these mysteries shape your perspective on the cosmos? Let me know your thoughts in the comments below. I'd love to hear your ideas and theories. And if you enjoyed this journey through the mysteries of the early universe, don't forget to subscribe and hit the notification bell so you never miss out on our next adventure into the wonders of space. The universe is full of secrets waiting to be uncovered, and together we'll keep exploring them. Until next time, stay curious.